Hi guys, so in this video we're going to go over how do we calculate the percentage uncertainty in the mass per unit length of a wire if we're given what the density's percentage uncertainty is and we're given the diameter of the wire, okay? So before we're going to go into this, we're going to look at what different ways would you see percentage uncertainty. So let's say I have an ammeter and I require practical, okay? Or maybe I'm revising for my paper 3 of AQA, or remember OCRA or Edexcel, they can ask you about these practical knowledge anywhere for the papers. So let's say we get a question that says, this is my ammeter. The ammeter reads 5.00 amps. I know if I want to take that reading as it is, I'm going to record the current to be 5.00 amps plus or minus 0.01 amps, right? Because that's the resolution in my equipment. The resolution tells me how accurate my reading is. So that reading is accurate to plus or minus 0.1 amps. So what that means is the reading might really be 5.01 amps or the reading might be 4.99 amps, right? It could be anywhere between those values. Okay, that's what the resolution means. It's how sure am I that that is my reading. So we can also find what the percentage uncertainty is. I want to find what the percentage uncertainty is. So I'm just going to write this for percentage uncertainty. What we do is we take the absolute uncertainty. So this is my absolute uncertainty. We divide it by our value, which is 5.00, and then we multiply by 100. So my calculator, if I was to do 0.01 divided by 5 and multiplied by 100, we're going to get a percentage uncertainty there of 0.2%, okay? So that was quite accurate, okay? It's quite good. 0.01 divided by 5 multiplied by 100, just double checking it. Okay, however, we know when we're doing experiments, we don't just take the read on the ammeter and that's us done, right? What we should do is we take repeat measurements. So let's say I take repeat measurements of my ammeter to kind of record what my current is each time, okay? So here is my readings for my current measured in amps. Again, what we do here is the reason that we repeat it, and we know that we must repeat it, is that because we want to see if there's any anomalies, okay? It's going to make it more reliable. So repeat our measurements to make it more reliable because we can notice if there's any anomalies. And what anomaly is, a result that doesn't make sense. So if I look here, clearly you can see that's definitely an anomaly, right? It's very different from the other results. So what we do is we ignore the anomalous result and then you just take your mean of the other numbers. So when I find what the actual value of current is, I just take the mean of these numbers. So remember, to find the mean of the numbers, all we do is we add them together. So 1, 2, 3, 4, 5. We're going to add all the numbers together, and then we're going to divide by the number of data I took, which is 5. So to find the mean, we're just going to do 5.01. We're going to add 5.05. We're going to add 5.09. We're going to add 4.93. We're going to add 4.92. And we divide by 5, and we end up getting the number 5. I'm not going to record 5 as my mean because, again, all of these are 2 decimal places. I'm going to record 5.00. Now I want to find what the absolute uncertainty is. The absolute uncertainty, when we take data now, doesn't become what it was in the equipment. It doesn't become the resolution of the equipment. What it becomes now is my absolute uncertainty is going to be half of the range. So what that means is I find the biggest number. Biggest number here is 5.09. We take away the smallest number. The smallest number here is 4.92. And we divide by 2. So what I do now is I do 5.09, take away 4.92, and I divide by 2 to figure out what my absolute uncertainty is. And my calculator says 0.085. Right? But I can't write 5.00 plus or minus 0.085 because it makes sense because there's only 2 decimal places here. So I need only 2 decimal places. It's going to be 0.09. Okay. Now, if you look at our question, it says, when I calculate the percentage uncertainty in the mass per unit length. So what we know is mu is equal to my mass per unit length, okay? It said that we're given the uncertainty and the density. So the uncertainty and the density is equal to 5.2%. And we're given the diameter of the wire is measured to be 6.25 millimeters, okay? So if I want to find out what the percentage uncertainty in mu is, clearly I need to know what the percentage uncertainty of the mass is and the percentage uncertainty in length. But I'm not given mass and length, I'm given density. So the first you should be thinking here is, how do I get density into this equation? And hopefully you're thinking density is equal to mass divided by volume. So what I can write now is my mass per unit length is my density, which is mass per unit volume. So again, mu is mass per unit length. but my density is mass per unit volume. So if we just look at that again, another way I can write mass is a density times a volume. So another way I can write mass is a density times a volume divided by a length. A volume divided by a length gives me an area. So it's the same way of writing density times an area. Okay, so it's going to be a wire. So remember, a wire we always know is like cylindrical in shape. So its area is just the area of a circle. The area of a circle is going to be pi r squared. Or because I know the radius of a circle is equal to half of the diameter, I can write that as pi times the diameter squared over 4. Because d over 2 squared becomes d squared over 4. So what I can write now is my mass per unit length is my density times by pi d squared over 4. So if I want to know my percentage uncertainty in mu is, I know that when we multiply things, you have to add percentage uncertainties. Okay, so again, when we multiply, we have to add the percentage uncertainties. Okay, so if I want to find the percentage uncertainty in mu, when I'm multiplying these, I need to add the percentage uncertainty in the density. I need to add it to the percentage uncertainty in my diameter. I don't have to worry about pi or 4 because they're constants. When you multiply or divide by a constant, the percentage uncertainty just stays the same. So that's why we can just ignore them. Okay, so I want to find my percentage uncertainty in my density and add it to my percentage uncertainty in my diameter. The percentage uncertainty in my density, I was told, was 5.2%. And I have to add it to the percentage uncertainty in my diameter. Okay, so I was given the value of my diameter, 6.25 millimeters. So what that tells me is the resolution of the equipment is 0.01 millimeters. So if I want to find the percentage uncertainty in that value of diameter, what I'm going to do is I take my absolute uncertainty, divide it by its actual value, and we multiply by 100. So what I do is 0.01, divide it by 6.25, and we're going to multiply by 100 to find out the percentage uncertainty in the diameter is going to come out at 0.16%. Okay, so that's my percentage uncertainty in my diameter is 0.16%. But hope you're thinking that's not just diameter here, it's diameter squared. And the rule is if we ever raise to a power, what you have to do is you have to do the power multiplied by that percentage uncertainty. So I have to take my power, which is 2, and multiply by my percentage uncertainty. So my percentage uncertainty diameter isn't actually 0.16, it's actually 0.16 multiplied by 2. So what I do now is 0.16 multiplied by 2, which gives me 0.32. So now I'm doing 5.2% plus 0.32%. And we do 5.2 plus 0.32%, I get a percentage uncertainty of mu to come out at 5.52%. And that's us finished.